Hello everyone. My name is Elizabeth, and our project is utilizing autonomous drones to identify fire hazards near power lines in remote areas. We are in McMahon's AVY group, and today Niru and I will be presenting. So, what's the problem? As many of you know, California, along with other states like Texas, have been experiencing a huge amount of wildfires over the last few years. A large portion of these fires were caused by the electrical distribution system, primarily issues regarding power lines. Over the last 3 years, Texas experienced over 4,000 wildfires caused solely by faults in electrical distribution. The Palisade Fire, caused by a tree falling into a PG&E tower, burned over 80,000 structures. We can clearly see that something needs to be done regarding the risks surrounding power lines. And so, what is our main goal? Our main goal is to prevent dangerous wildfires like the ones in California and that are often linked to power lines from companies like PG&E. We strive to do this by using our drone combined with our machine learning model. And these drones will help us find vegetation that are likely to cause fire. Ultimately, we aim to accurately figure out the risk of a large wildfire and then tell the right people so that they can take the action. And so these are some examples of threats we plan to address. There are several critical risk factors our drones want to identify. One concern is unstable trees and brush. These can collapse due to high winds or structural weaknesses, and they frequently cause power outages when they fall onto power lines. Another risk is arcing conductors, which are electrical discharges that occur when current flows through unintended paths, often due to vegetation making contact with multiple power lines. For example, a branch bridging two conductors can trigger a surge in current, which could lead to ignition of the branch. Additionally, we also plan to identify invasive or encroaching vegetation near power lines. Such vegetation, especially when dry or dead, can act as fuel to fires, and even without direct contact, arcing between high voltage lines and nearby ground vegetation can occur, which sparks fires. We also account for damaged power line components such as cracked insulators or frayed wires, which can produce sparks or fail under stress, increasing the risk of ignition. By equipping our drones with the ability to detect these specific threats, we aim to support proactive wildfire prevention and infrastructure resilience efforts. So, some of the key important factors of our project is that we intend it to be fully autonomous and designed for real-time fire risk detection, requiring no manual control or internet connection, and our GPS will automatically flag and log hazards. Makes it more proactive than existing solutions, and also unlike most current efforts that focus solely on inspecting distribution poles, we want to focus on the surrounding vegetation as well. And using high resolution imagery and potentially infrared scans, the drone can also assess the stability of nearby trees. Ultimately, by detecting these threats early on, our system and drone offers a preventative solution to reduce both wildfire risks and power outages. And so, why did we choose drones? Our decision to use drones for power line inspection is because they are significantly more advantage over traditional manual methods. Manual inspections have been the norm, but they are time consuming and extremely challenging to execute in remote or rural areas. And they pose safety risks to workers. Drones, on the other hand, offer accessibility, allowing for the inspection of power lines in areas that are difficult or dangerous for humans to reach. This enhanced accessibility means greater efficiency, and a single drone can inspect a far greater length of power line in the same amount of time it would take a human to inspect just one. Ultimately, drones represent the most effective and cost-efficient solution for surveying power lines, providing a more efficient, effective, and accessible approach to risk mitigation. And here are some current related projects. PG&E wildfire safety programs and initiatives, they focus on reducing the potential for catastrophic wildfires related to electrical equipment, which would reduce the potential for fires to spread. The RIDI program enhances the evaluation of SDG&E's overhead electrical power line and equipment within identified high fire threat risk district areas. There's also the Excel's Energy UAV program, EPRI drone initiative, and SE wildlife mitigation, and they all are directed to mitigating wildfire risks.
So let's now move on to our hardware, which is basically our actual drone and parts. So I want to first talk about our drone kit. So we chose the Holybro X500 V2 ARF drone kit because it provides a lightweight but strong carbon fiber frame, ideal for stability. And it has a modular layout, letting us integrate custom components, and is also highly compatible with a variety of flight controllers. This flexibility allows us to test different setups and iterate very quickly. And for fire prevention in real-world conditions, having a durable and responsive frame is essential. Now, I want to talk about its measurements and specifics. So our wheelbase is 500 millimeters, and this is basically the distance between opposite motors on the drone, measuring diagonally. A 500 millimeter wheelbase indicates the medium to large drone, which helps with stability and low capacity. Our mount pattern is a 16 by 16 millimeter. So this refers to the spacing of mounting holes used to attach the motors to the frame. And a 16 by 16 millimeter is a standard motor mount size compatible with many brushless motors, allowing for flexibility in motor selection. Our landing gear height is 215 millimeters, and this is how tall the landing gear is from the bottom of our drone to the frame to the ground. And at 250 millimeters, it provides enough clearance to carry sensors or a payload underneath without hitting the ground during landing. The weight of the overall drone is 610 grams. This is just empty frame weight without motors, batteries, or payload. A lighter frame helps with flight efficiency, and but also needs to be strong enough to support other components. And the payload it can carry is 1,500 grams. So this is basically the maximum additional weight the drone can safely carry. In our case, 1,500 grams allows us to attach things like sensors, cameras, or communication equipment for hazard detection near power lines. The flight time is 15 minutes, just the hardware, and the battery is a 4S LiPo battery. 4S means the battery has 4 cells in a series, and LiPo stands for lithium polymer. So we also included several important components to make the drone more functional. A lithium polymer battery for power, a Raspberry Pi for onboard computation, a high resolution camera for object detection, a battery GPS IMU for location orientation, a telemetry radio for real-time updates, and a receiver plus transmitter pair for manual overrides. So, for our current state of the drone, we've successfully assembled the major components and are now focusing on getting the camera fully integrated, achieving stable flight without potential flight failures, testing GPS and telemetry with remote commands, and preparing for field trials in open areas. So far, we are seeing stable responses and successful waypoints in following test environments. But in the future, we do want to make sure that we get a license so we can take more images. So now I want to talk a little bit about the software that actually allows us to interact with our drone directly. Q Ground Control. So Q Ground Control, or QCG, is a powerful open source ground control station software that connects to the drone's flight controller via radio telemetry or USB. It acts as a bridge between us, the users, and the autonomous system in flight. And there's several reasons we have relied on QCG. For one, flight planning. We can pre-program the drone's path using GPS waypoints. This means we tell the drone where to go, how fast to fly, how high to stay, and when to stop or land before it even takes off. We also use it for real-time monitoring. So QCG basically provides us a live feed of drone diagnostics, its altitude, speed, GPS location, battery status, and sensor calibration. We monitor everything mid-flight, which is especially important for safety and data validation. Our third reason for using it is our sensor calibration. So before our flight, we calibrate the compass, accelerometer, GPS, and magnetometer through QCG to ensure the drone interprets its surroundings accurately. This is critical for a stable autonomous flight, especially when flying in environments with magnetic interference, especially with power lines. And lastly, we use it for a fail-safe setup. We use QCG to define what happens if something goes wrong. For instance, if the GPS signal is lost or the battery drops too low, the drone is programmed to return to launch or safely land. So basically, think of QCG as our mission command center. It's where the drone, it's where the human input really ends and the autonomous flight begins. So while a drone can fly without human control, QCG ensures that it does with precision, safety, and flexibility. So here is just the user interface of QCG and kind of the way we navigate it. So now moving on to our software components. So here's a closer look to how our software actually detects and interprets our pilot risks. So we basically use a multi-layer processing system, starting with a camera input. So the camera basically captures frames in real time, transmitting them directly to the Raspberry Pi. Our second layer is TensorFlow's object detection CNN. So this AI model basically classifies objects in each image. It's trained to identify power lines, trees, branches, poles, and other critical components. We've trained it on thousands of labeled images so we can distinguish it between dangerous and safe scenes, and we're still continuing to test and train it. And our third layer is our hazard logic. If the software detects that vegetation is within critical distance of power lines, or sees signs like leaning trees or hanging branches, it flags the image as a hazard. This flag will include GPS coordinates, drone altitude, camera angle, and object type, for example, branch wire or pole. And our last layer is data storage and alert preparation. So all flagged images and data are saved in the Pi storage, ready to be uploaded when a connection is available or delivered directly via telemetry if needed. This entire loop happens within just a few seconds per frame, enabling real-time risk detection without the need for human review. Now, I also want to talk about a previous model we created, the red flag method, which is basically a system we originally designed to detect and label potential fire hazards automatically. It was basically created like this. We trained a machine learning model using a labeled data set of images, some with trees dangerously close to power lines and others where vegetation is safely distanced. Features like leaning trees, hanging branches, or intersecting vegetation were marked and used to teach the model what constitutes as a fire risk. And when the drone flies, it uses this trained model to scan each frame in real time and detects if it detects a high risk object, it flags it as a red hazard. Now, it then logs critical information like GPS coordinates, time, and object for follow-up. So the idea is to basically make detection fast and autonomous, but it's different than our current version because we've now changed to using TensorFlow CNN.
So we are also using generative AI as a part of our data set, and this approach allows us to provide a more extensive and diverse set of visual examples for the model to learn from. However, there's also challenges using generative AI. While some generated images portray photorealism, others exhibit characteristics that deviate significantly from real-world distributions. For instance, as observed with the top right example, some outputs can be highly fantasy-like or contain objects inconsistent with our target environments. This data can also lead to training risks because it introduces noise and model bias. This can ultimately degrade the model's generalization capabilities and reduce its accuracy when deployed in real-world scenarios. Therefore, we still have to filter the generated images to ensure only high-quality data contributes to the training pipeline. And as we continue with our project, we have some possible roadblocks. First, accurately identifying and assessing the many fire risk factors require extensive data and a strong machine learning model. And making data acquisition and model training have been our main challenges so far. Second, standard cameras struggle with dense tree covers, limiting navigation and risk detection. Assessing tree stability also demands advanced complex algorithms and sensors. And finally, if there is difficult weather like rain or strong winds or fog, this can also damage the acquisition of high quality image data needed for our model. And so these are our future actions. We intend to test at local parks to ensure the drone's reliability and safety of the aerial vehicle. These test flights will allow us to collect real world data in addition to our generated ones. And our ML model is still in development. Once it's done, we also will have a drones license to operate it in public and rural areas. This will allow us to enable a broader deployment and more comprehensive data collection in different environments. Also, we intend to make our drone autonomous, fully autonomous, and this will enhance efficiency and reduce human intervention. Looking even further ahead, we want to potentially develop sensing capabilities to assess the structural stability of surrounding trees, and this will determine tree health and identify dead or unstable vegetation, thereby providing an even more skilled risk assessment. So these are our acknowledgements. We would like to thank ASDRP and Dr. McMahon for providing us with the resources and support needed for our project. Any questions?